Okay, so this next section has to deal with the movements of the seas. There are three primary types of water movement in the ocean specifically, and these are ocean currents, waves, and tides. Ocean currents is a large stream of ocean water that flows at or below the surface. And actually, they weren't discovered until relatively recently in Earth's history. I believe it was during the 1700s. I might have the time frame a little bit wrong there. But it was a British admiral. He was sick and at home recovering from his illness, and his daughter was reading to him out of the Bible. And she actually gets to a passage in Psalms, and the phrase "pathways of the seas" is used in that psalm. And this British admiral, who had been in the Navy many years, most of his life, and he thought to himself, I have never seen a pathway of the sea. Prior to this time, ships stayed pretty close to shore. They kept shore or land within sight. This made for some very long voyages because they couldn't go very far away from that. And so this British admiral, proceeded to study the ocean currents, and this was really the first comprehensive study that we have of the currents. The first type of current is the surface current. These are large masses of water that flow horizontally along the surface of the oceans. These are probably what you thought of when I said the word current. These are caused by prevailing winds constantly blowing over the surface. There could be some other factors involved here, but these prevailing winds are the primary factors. They are blowing water in a direction, the winds come along, they hit the water, and these prevailing winds are pretty much generally in the same area, around the same speed, going the same direction all the time. One effect on these currents, the wind is moving it horizontally, but there's an effect called a gyre, and this is a circular path of the currents caused by the Earth's rotation. The winds are pushing it one way because the Earth is moving, it's rotating, it's actually causing the water to flow slightly to the side. So it gives it a somewhat circular motion. One of the more prominent currents here near the United States, is the Gulf Stream or the Gulf Current. It is a warm surface current. Starts off the coast of Florida, down there by the southern tip of Florida, coming up the southeastern United States, and I think it's around the Carolinas. It kind of shoots off into the ocean, the Atlantic Ocean there. The Gulf Stream is partly responsible for the mild climate of Great Britain and a lot of the other areas a lot of the other regions in that area. Another large current around the Americas here is the Peru Current, also called the Humboldt Current. It's a cold current that flows northward along the Pacific coast of Peru, keeping things a little bit cooler in that area. There are subsurface currents. These are ocean currents that flow beneath the surface. Some of them are deep ocean currents. If you've seen Finding Nemo, they have the EAC, the East Australian Current, and that one, as depicted in the movie, is actually somewhat below the surface. It's not deep, but it's definitely below the surface of the water there. There are also density currents. These are currents that result from a difference in density. There's a difference in densities between two groupings of water. There will be movement. Because if one is less dense, it'll move over it. This will cause other water to move in. Different densities can also move by each other depending on the geography under the water. Such like that. A turbidity current is actually almost kind of a density current, except they are more specific to the mouth of rivers. These result from the mixture of mud or silt with seawater. The water sinks and flows along the bottom of the ocean until it evens out, if it does at all, becoming part of other masses of water. Upwellings are kind of going the other direction. These are deeper, cooler waters that have suddenly become less dense. They flow upward to the surface. The cool waters of upwellings usually provide a lot of nutrients to the organisms that are living there, taking it from the bottom of the ocean to the upper areas. And then there are countercurrents. This is a current that flows in the opposite direction, either beside, on top of, or beneath the surface current. They're not considered currents because the current is actually what's causing the countercurrent. The current is moving in one direction, taking water out of an area, And if it's taking water out of an area by movement there, then water has to move into that area. And the countercurrent is the water moving in and replacing the water that is moving out because of the current. Waves. These are rhythmic back and forth motions of water that transfer energy through the water. Back when several chapters ago when we were talking about earthquakes, we also mentioned tsunamis and looked at that a little bit. And energy can be transferred through water. The tsunami in the Philippines caused by the earthquake, such a large earthquake, the energy actually reached California. Now, by the time it reached California, it was greatly reduced, only added like a foot or two to the height of waves. Not real dramatic at all there. Closer to home, that energy resulted in a lot higher waves in the Philippines and Indonesia area there. But some of the anatomy of a wave. When I said wave, you probably got a picture in your head, and you probably pictured the crest. This is the highest point of a wave. Then there's the trough, the lowest point of the wave between two crests. The period is the length of time between one crest and the next. If you're out in the ocean playing and you have the waves there, the period is the time between you get picked up by one wave and then the next wave comes and picks you up. Wave formation. How do waves form? Well, most waves are created by wind blowing along the surface of the water. This is why you can have waves even in lakes where there is no current. The wind just blows it, kind of piles it up, picks it up a little bit, pushing it together. Depending on how strong the wind is, determines what kind of waves we see. Choppy are waves that are of different sizes and move in various directions. So you have all sorts of wind coming into the area from many different directions, resulting in uneven wave formation, some of the waves colliding together, and you just get some kind of just harsh water, basically. White caps are white foamy crests on top of waves. Generally, what's going on there is the wave is being picked up, but the wind is kind of strong, and it's actually blasting the top of that thin part of that crest, causing this white foamy crest. And then when the winds are calm, we can have ocean swells, gentle rolling waves. Gentle winds might cause ocean swells. Also, because of other things that can affect it, we can have it during calm weather. You can have an ocean swell even when there is no wind. So that gentle rolling wave that just rolls under a boat. Continuing on with wave motion here, what can waves do? Well, we have the breaker. This is a wave that nears the shore, and it kind of gets, as it hits that sandy bottom, it starts building up because the water on top is a little bit faster. So it keeps building up and building up depending on the contours of the seafloor at that time. Eventually toppling forward, forming a wave with a white crest. And these are the waves you probably thought of, are breakers. Surfers like breakers. They like big breakers because they can do all their acrobatics and stuff with them. The actual surf is a mass of foaming water washing up on the beach. Really what happens after the breaker topples forward. And you have all that water just coming up the shallow part of that beach there. Surf is a powerful agent of erosion. The beaches are constantly getting rearranged because of surf beating them up, taking sand away, and so on. Now, as a result of some of the contours and geography near beaches, we get some interesting currents there. One is the undertow. This is receding seawater at the beach that flows as a thin sheet along the sea floor beneath incoming swells and breakers. As those waves come in, that water needs to get back out. And as those waves come in, a thin sheet of water goes out underneath all of those waves that are coming in, taking that water back out to ocean. Undertows are nasty to be caught in because they can be strong and powerful, sweeping swimmers under the water. And if you're an air-breathing person, being under the water is problematic. There's also the longshore current. This is a little bit similar to the undertow, except for the location. This is outflowing water, so water going back out to sea, trapped near the shore by a sandbar. The water came in over the sandbar. Now it's trapped near the shore, causing it to flow parallel to the beach. In Oregon, we do have a lot of sandbars out there, and you have to be careful with longshore current. These flow parallel to the beach. So you might be playing in the ocean, just minding your own business. Nothing's really going wrong. But eventually you look up and you realize you are actually further down the beach than when you started. And it's not because you were walking. This longshore current just gradually took you along. Longshore currents, if that's all that's there, not a huge problem other than just being slightly lost. Now, the dangerous part of a longshore current can be associated with a rip current or a rip tide even. A dangerous surface current caused by large volumes of water flowing rapidly through a narrow channel in a sandbar. And this is flowing rapidly back out to sea. A lot of times when people say I got caught in an undertow, what they really got caught in was a rip current because it didn't actually pull them underwater. Rip currents are near the surface. I've known many people to get stuck in them. I've gotten stuck in them a little bit myself. And they are hard. They are strong, and they will tire a person out. The best way to get out of a rip current is not to swim against it, but to swim sideways. It's through a narrow channel. So once you get out of that channel, it's no longer dragging you out to sea. There are many people yearly that are saved by the Coast Guard from rip currents and undertows, actually. Tsunamis are the largest known waves. Almost 90% of all tsunamis result from strong earthquakes. Because of how devastating tsunamis can be, they've developed the Tsunami Early Warning System, a string of sensors out in the ocean to let nearby islands and land masses know that energy is building up and it's going to result in water coming up onto the coast. Indonesia, Philippines, India, those places all have tsunami warning systems. Hawaii, I'm sure, also does. Florida does. So just because those places are pretty low lying. If it's a large enough tsunami, some islands can just suddenly disappear until the water level goes back to normal. Tides are the most regular and predictable movements of water in the ocean. These are caused by the pull of the moon's gravity. We're most common to the idea of high tide and low tide. High tide is when the ocean levels are the highest. Low tide is when they're the lowest. Now, it doesn't always just happen as one high tide and one low tide a day. If you're in an area that does, that's called a diurnal tide. One high tide and one low tide each day. But there are other combinations. Semi-diurnal, 2 high tides, 2 low tides each day. And they reach the same level. So the 2 high tides are equally high, the 2 low tides are equally low. Then there's the mixed semi-diurnal, 2 high tides and 2 low tides that reach different levels. So the 2 high tides can be separated by as much as feet. The 2 low tides, same thing, could be a difference of as much as feet. So just different, or reaching different levels on that mixed semi-diurnal. Now there's a couple of special tides that we don't see as often because certain events need to happen. There's the spring tide. Sun and moon are in line with the earth, so the moon's gravity and the sun's gravity are all pulling in the same direction. And this results in higher tides than normal. And this has actually come in to effect in wartime. During the Korean War, the American embassy and the Marines had gotten beaten back and they were under heavy fire. And to get the American military in there was tricky because the North Koreans, Chinese, had fortified a lot of these areas, making them extremely difficult to land an invasion force at to give relief to the soldiers that were there. So General Douglas MacArthur, as well as some of his aides, were looking through charts. They were trying to figure out, it's like, they wanted to be able, if they could, get behind the North Korean army line and cut it off from its supply. That would have been wonderful. They started looking at places to do this, and one of the places that popped up was Incheon Harbor. There was only one problem with Incheon Harbor, and that is it was too shallow. The warships would not be able to float into Incheon Harbor. They would go to ground before they could get to the landing areas. However, they started realizing that it would have been a spring tide soon. And they did some calculations and realized that that spring tide would add just enough depth to the harbor that the warships could get in for a small period of time, a couple of hours, if I remember right. And so that's exactly what General Douglas MacArthur had done. They invaded at Incheon. Casualties, as far as those things go, were minimal. And they were able to cut the country of Korea in half, or the peninsula of Korea in half. They were able to give relief to the Marines. They cut off the supplies. they actually were able to chase the North Korean army back. I think it was to the Yalu River in northern Korea. And it was a very successful because they knew about spring tides. Now, kind of the opposite of a spring tide is a neap tide. And that is when the sun, moon, and earth form a 90-degree angle. So, and you see that in the chart right there. It could be on either side of the earth, doesn't matter. And this results in weaker than normal tides because the sun is pulling water towards it, the moon is pulling water towards it, and they kind of cancel each other out. So these are neap tides, these weaker than normal water. Now, you need to go answer the science video question. If you do that, there will be a Classcraft reward, as well as something in the watcher schedule on the RedWeb. I will see you the next class.